Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And we're doing a little mini-series in one-way fixed effects ANOVA, and we're on part 9, which deals with orthogonal contrasts. Now, this is the R illustration of part 9, where part 9 we did more of a lecture-based series. So here, we're assuming that you have gone through the first 8 parts, and so I'm going to run those. And throughout this little mini series, or the illustrations using R, we're using an example by Montgomery in a book titled Design and Analysis of Experiments. The third edition, we're looking at example 3.1 of tensile strength experiment. And tensile strength is, how much force or does it take to tear something apart. And we're looking at fabrics with different cotton blends in it. So one fabric had a 15% cotton blend, another had a 20% cotton blend, 25, 30, and 35. So let me run these. And so these are all the previous lectures or videos we've done, and now we're on part 9. And here I sort of semi-randomly create 4 contrasts. Now, contrast is, it's a linear combination of the treatment parameters, the tau 1 through tau 5. There's 5 treatments, and the coefficients have to sum to 0. So here, we have 1 and minus 1, that's 0. Here we have 2 and minus 2, that's 0. So each of these coefficients sum to 0, so they are contrast, and we've shown that all contrasts are estimable, meaning we can recreate them with the linear combination of the row space. And so let's actually do that first. So here are the contrasts. We're going to put them in C1, C2, C3, C4, and now we create these row vectors, which are the coefficients that were taken to create a linear combination of the row space. Now, if it's part of the row space, we can create a lambda 1. So this row 1, to recreate this C1, or lambda 1, sometimes we call it in the lecture videos, but I do it in a very specific way. I take this first contrast, the coefficient, divide it by 5, the number of replicates, and then rep it 5 times. So I rep C1 over N 5 times, C2 over N 5 times, C3 over N 5 times, etc. And I do that for each of these because then it creates a very unique outcome that makes these calculations a little easier. And in the lecture videos, we talk about it very explicitly. Now let's show that they are orthogonal, and they're orthogonal if you take the dot product of between any 2 vectors and it's 0. So we create a matrix where the columns are those contrasts. So we take the transpose times itself, and this is the matrix we get. So when we take contrast 1 times contrast 1, we get 2, and then contrast 1 times any other contrast, we get 0. And the same goes for all the other contrasts. So they are orthogonal. Now, we did develop another way to see that they are orthogonal, and that's if we take the row vector, so row 1 times m times row 2, or any other row. If they were 0, then that's also a sign that they're independent. But you have to go through each case. So we take row 1 times m row 2, row 1, row 3, row 1, row 4, and notice that each of these are 0, or essentially 0. And then let's take row 2 times 3 and 4, and they're essentially 0, and they're essentially 0. So that is actually theorem 1 in part 9, where we go through how to derive and show that the contrasts are orthogonal. Now, theorem 2 deals with I'm going to sneeze. Oh, excuse me. So it deals with showing that the row 1, 2, 3, and 4 actually sum to 0. And that's what we show here, that each of these, j times the row vector is 0. And this is essentially 0. There's some rounding error in the computer. So that was theorem 2 in the video. Now theorem 3 deals with showing that MP, or M, which is the perpendicular projection matrix on the column space of X, times rho, in our case P, it's part of the column space of M minus J. Now M minus J is a perpendicular projection matrix onto the orthogonal complement space of the column space of 1, but it lives in the column space of M, and the column space of M is equivalent to the column space of X. So whenever we pre-multiply a vector, a dangling y vector, any vector, times this, it shoves it down into this space. And here we show, here, the first step here, we're showing that M times rho 1 is actually rho 1. And we've chosen, or defined rho 1 in this specific way so this happens. But it turns out that any row that satisfies the condition that its linear combination of the row space is equal to that lambda 1 vector, then we get this unique representation back. Now here, if we pre-multiply a vector times this perpendicular projection matrix and we get it back, that means it actually lives in this column space. And that was the theorem 1. And if we look at this, notice that the first 15 components are 0, or essentially 0 in computer language, and the next is minus 0.2. And that's what this vector is. These two vectors up here are. So it does live in the column space of M minus J. Now theorem 4, we showed that capital P star times capital P star prime is actually equal to this perpendicular projection matrix. And to me, this is pretty cool because it gives us an idea of the structure of what this perpendicular projection matrix is. But how we define P star, which we'll just call capital P in R, we take each of those row vectors, row 1, 2, 3, and 4, divide it by its length. So this is the first column in this matrix P that we're creating. And then we do that the same way. So we have row 2 divided by its length, which is this. And we do that for all 4. So let's store that in P. And now let's take P transpose P to show you that they are orthogonal with the length of 1. So notice the diagonal is 1 and all the off diagonals are 0. So they are orthogonal. That has a length of 1. Some might call them orthonormal. That's fine. Now let's show that P times P transpose is equal to M minus J. Now in previous videos I've already defined M, which is perpendicular projection matrix on the column space of X, and J, capital J, is the perpendicular projection matrix on the column space of 1. So let's run it in this function, and it compares each component with the other component, and they are all equal. So it returns a true. And that was what we wanted to show in theorem 4. Now, the next video, we take these orthogonal contrasts and we show how to partition the sum of squares treatment. And that's the topic of part 10. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.